Hey everybody, we're going to do an introduction today of some game theory terms. Our textbook begins with some interesting activities, all right? And I want to point this out. If you really want to understand game theory, we're going to start, the very next lesson is going to start with the calculations, where we actually do mathematical operations and we calculate the solutions to these games. But to do so, it would help if you actually worked through the activities, okay? And I know there are 11 activities in the beginning of chapter 2, but why am I suggesting it? Well, I just think it'll be helpful for you, right? That first of all, the book is written from a discovery perspective, so the examples start off very simple, very straightforward, and then they add some additional complexity to demonstrate certain features of games that we want to focus on, right? So it's going to help a lot to take a few minutes and to go through those examples and maybe even get out a scrap piece of paper and do some calculations, do some write down the results of your analysis and then check to see if the book seems to agree with you. So that's what you should do if you really want to understand the content very well. So, the first thing I want to talk about is the players. And with game theory, a lot of times we're thinking of human beings being the players, but it turns out that we just mean the actors, the beings that are acting. For example, nature. We can play a game where random chance plays a role. For example, blackjack. Games against nature really did start meaning nature, where we might be talking about the wind or the tides. Or the rainstorms, right? That might be the actor in the game. Um, and even in games like poker, where there's a piece of the game that's unknowable because of random chance, the dealing of the cards is random, and that influences the strategies or the possible outcomes. So that's what we mean by the players. Um, it's not a problem to have random chance involved in a game. It can make things interesting. And I will also mention this. Um, Poker pros are good at two things. They're good at the psychology of the game, and they're good at the mathematics of the game. And there's this expression that gets shortened to an acronym, GTO, for Game Theory Optimal. And again, these poker players may not know it down to the hundredth of a decimal place, but they do know these probabilities. They do know the mathematics of poker. They do know the game theoretical optimal play, given that that they know what the cards are, right? If they knew exactly what you were holding, they know the game theory optimal play. They have a guess about what you're holding based on your reactions to the hand so far. And anyway, so game theory optimal is talking more about the theory of the game, but trust me, all poker pros know it or have a working knowledge of it. All right, so player opposition, what do we mean by that? We mean that the players are not colluding. And we can study collusion and cooperation. So collusion is the economics term when it's either illegal or frowned upon or both, when two companies are colluding to keep the price high, thereby earning the benefits of a monopoly, even though there's two companies, let's say, providing this good or service. Um, so we, generally speaking, in economic theory, want to avoid collusion, right? But there are times where the game might, well, first of all, how we play the game is certainly going to change if we're allowed to cooperate. And that's coming later. For the moment, we're going to say that these players are perfectly opposed. That, like poker, if I win $1, somebody at the table has lost $1. If I lose $2, somebody at the table has won $2. We're opposed in our goals, perfectly opposed in our goals. Okay? And the rational play principle, now your book doesn't exactly call it this, but our author, Dr. Jennifer Nordstrom, is very clear that there are two principles, and she's describing the rational play principle. The players are self-interested. Okay, they are selfish beings who want to do what's best for them. They're not altruistic, hoping to help out the other player. Oh, if I could win a little less, but then my opponent could win. No, no, that is not how these players are thinking. These players are, how can I maximize what I get? That also means, generally speaking, in these zero-sum games, they'll also be interested in minimizing what the other player gets, right? So those two things are happening. The second piece of the rational play principle is that the players are perfectly rational. So we're assuming that they can do the mathematics involved in the game, they can understand the logic, they will make the precise best move at any given time they have to act. Whenever our opponent acts, whenever any of the players in the game act, they're going to act in their own self-interest, and they're going to act with perfect rationality. Okay, so that actually helps with our analysis. We don't have to worry about, oh, what if they make a mistake? What if their play isn't optimal? No, we can analyze optimal play from both players' perspective. So the rational play principle and the two components there are self-interest and perfectly rational. So when we talk about strategy and game theory, what we mean is we're going to specify how we're going to act in every single point at which in the game we get to act, right? So we have to have contingencies because the other player may not always play the same way, right? So our strategy means that we have to know exactly what we're going to do when we play the game. Now, for matrix games, this is a lot easier to see. Now, this is a matrix game where the row player and the column player each have two strategies. Okay? And again, using the Strafen convention that the player that's playing the column strategies, we'll call that Colin, and the player that's playing the row strategies, we'll call her Rose. And again, Colin can play either A or B, and Rose can play either A or B. And it turns out that this is a game with a mixed strategy solution. So I'd introduced the term pure strategy solution, but now we're talking about a mixed strategy solution. And let me just erase that and let's go forward and see what we got. First of all, a strategy here, and these are the optimal strategies. If you do the calculations for this game, the optimal strategies is that Rose should play strategy A 5/9 of the time, and she should play B 4/9 of the time. Now, what we're going to assume is that Rose has some way of randomizing. And yes, it is difficult to write a perfectly mathematically random number generator. But we're assuming that she has a way to do so, to generate a random number, and based on that random number generator, Rose is going to play 5/9, 4/9. Okay, so that vector R is just a list of her strategies. Now, if you remember, I mentioned this, that the sum of the fractions has to add up to 1, and all the fractions are between 0 and 1. So, by the way, it's okay if Rose has an optimal strategy set of 0, 1. That means that she should never play strategy A, and she should always play strategy B. So that's not impossible. Even pure strategy solutions can be written as vectors, all right? And of course, we're saying that Colin should play 1/3 A and 2/3 B. All right, so again, this is a little bit of preview of coming attractions. I wanted you to see how it looks. So let's take that and move along. And in this case, and sorry that that's getting cut off a little bit at the bottom, but both strategies are active for both players. Like I said, a mixed strategy solution. And the proportions that I've given, the 5/9, 4/9, the 1/3, 2/3, those are exact for the game. And we'll talk later on this week about how to do those calculations. Okay. So what's a solution to a game then? Okay, so a solution to a game is going to have three things. Okay, it's going to have Rose's optimal strategy set, and a lot of times we'll use a row vector. for our optimal strategy sets. It's going to have an optimal strategy set for Colin, and it's going to report the value of the game. Now remember, this is the condensed form. In other words, here we're representing Rose's payoffs, right? So if Rose plays A and Colin plays B, that gets a payoff to Rose of 4 and therefore a payoff to Colin of -4. Remember, these are zero-sum games, and if I always present Rose's outcome values in the matrix, then I can use the opposite to find Colin's. So you have to remember Colin in this case is trying to minimize. He wants the lowest value. Why? Well, because his values are the opposite, right? And if he can get Rose into a negative number payoff, then that's a positive number for him. So that's hard to remember sometimes, but Rose is trying to maximize while Colin is trying to minimize in this condensed version of the game. And let me get rid of the scribbles there. And all right, so game matrices. I wanted to show you these two versions. They come straight from the book. And Dr. Nordstrom calls it the matching pennies game, right? And basically you're flipping two coins. And I forget, I think when, let's see, heads, if they match, Rose wins, right? If they match, Rose wins. So heads, and tails. Tails is 1 to the row player. And heads, tails is -1 to the row player. Yeah, so Rose is winning when the coins match. They're both heads or both tails. And if they're opposite outcomes, one heads, one tails, then Colin wins. And we will use this setup a lot more later in the course, right? But this is the extended form that shows the payouts for Rose and Colin both as XY coordinate pairs. And the X coordinate is Rose's value, the outcome that Rose will earn, and the Y coordinate shows Colin's outcome. Okay, and again, this is why we can have condensed form, because if Rose is winning 1, Colin is losing 1. If Colin is winning 1, Rose is losing 1, right? So because of that opposites nature in a zero-sum game, right, we have the condensed form. All right. And you'll see this a lot. Most of the time, you won't see the extended form. You'll just see the condensed form. That's how we analyze these matrix games, especially zero sum. Now, speaking of that, we have constant sum games. All right. Now, some other game theory textbooks separate the two. They have zero sum games and constant sum games. Now, all textbooks pretty much agree that they're going to be solved in equivalent ways, right? But this book calls them the same thing. So Dr. Nordstrom specifically refers to constant sum games as zero sum games. All right, so just note that when the book talks about them, she will call them the constant sum games. She won't give them that term. She'll call them zero sum games. So just be prepared for that. Look through the example that she gives and understand how she's going to refer to that. Okay? And so that's a quick overview of the key terms. Again, I do want you to do those activities that I pointed out, but let's glance at the accompanying notebook in our data hub. So what do I want to put here? Well, what is meant by the term player? And put this in your own words, but remember, the players aren't necessarily humans. The players are the beings or entities that are acting in the game, like a game against nature, like random chance. Sometimes even in the stock market, we can think of the stock market and these stock prices going up or down as a random walk. They even use that term, economists do, a random walk. And so nature is kind of playing against us in that setting, right? We're trying to win money by investing well and profitably. but the other actor, the other player in the game is nature or the stock market. Okay, so put that in your own words. Rational play principle, there are two pieces, remember? One of them, the second one was listed, is that the players are going to be perfectly rational. So we can mathematically predict with logic and calculations what the optimal play will be and assume that these players will know that, will figure that out, and will play that way. And also remember self-interest. There is no cooperation at the moment, no collusion. Their interests are perfectly opposed. Strategy, what do we mean when we refer to players' strategy? So again, in these matrix games, they'll have two, three, four options for strategies they can play, and they may be mixed strategies. We may not have a pure strategy, like we can't say, oh, Rose will play strategy C all of the time. Well, maybe she'll play strategy C some of the time and strategy D some of the time, but maybe A and B are not active. She will play those 0% of the time. So our strategy means that we can list the percentage or the proportion of the time that she's going to play each of her strategies, and same for Colin. That's what we mean by strategy, a complete description of when and how she's going to play or how Colin's going to play. Information, okay? I slipped past this a little bit, and you can read in the book, the textbook, but there are two kinds of games of perfect information and games of imperfect information. And it's real easy to explain. The game of chess or the game of checkers is a game of perfect information. Both players can see the whole board, they see all the pieces. You don't know exactly what your opponent is planning to do, right? But you can see all the possible moves and you can calculate which of the moves would be better or worse. So chess and checkers are games of perfect information. Games of imperfect information are games like blackjack or poker, Texas Hold'em, right? In blackjack, there's a hole card, and you can't see that hole card until you've already made your bet. The dealer has a hole card, and you see half their holding, right? And so that's a game of imperfect information where you're making decisions, you're taking actions without knowing exactly everything. And the same thing in poker with Texas Hold'em, you have two hole cards and five community cards on the board, but you can't see anybody else's hole cards and they can't see yours. So the players are acting with imperfect information. So those are the two types, perfect information and games of, well, perfect or imperfect information. And what do we mean when we say we've found a solution to the game? And we need three things. We need Rose's optimal strategy set, we need Colin's optimal strategy set, and we need the value of the game, which we usually report. When we just report V equals, we're reporting the value of the game, we're going to report it from Rose's perspective. But of course, we'll be able to calculate what Colin's is. When we get to non-zero sum games, we might have to add both Rose's value and Colin's value, because if it's not zero sum, there may be it may not be clear exactly how to calculate what the outcome is going to be to Colin if we only know Rose's outcome. All right, so again, here I just provided some space for you guys to take notes, and I'll be back soon with some calculations, and we'll talk about how to find some solutions to these zero-sum games.